balance the expansion of the universe. So I have a constant interpolar distance between them. And the speed I will give to them depends on how far they are from each other and on the rate of the expansion of the universe. Okay. So I have two quarks, but they are now moving towards each other, just to counterbalance the expansion of the universe. Now, I will skip this part. I just tell you that everything you move here, everything you read here, it has to be the geodesic distance, right? So the geodesic distance is not the same. This is in the flat space-time, and this is what I will use when I am in a curved space-time. But I can find the string velocity that I was telling you here. So this minimal surface can be found by doing this computation. Right? I just do this parameterization. Here is the velocity of to the quarks I give, and here is the bulk profile of the string. So if I do that, I will get a time-independent minimal surface, and it's an ordinary differential equation. Okay, I'm not showing you anything, I'll just show you the results. So here is the profile of the string solutions. Here you see, here is my quarks, this is my boundary of the theory, this is my bulk, here is where I put the quark and the quark, and this is for different distances. You see how the profile of the string changes in the bulk. Now, if you want to see it in a better way, let me go to this one. I pick only two. You see that I have two solutions with the same boundary conditions. Here is my boundary. But they have two different minimal surfaces. Now, this minimal surface, you see, is distorted somehow from the expansion of the universe. And this is a bit less distorted. And this goes deeper to the bulk. So this is exactly what happened. This is similar to what happens when you have a normal black hole. Here we don't have black hole, we have an expanding universe. But the only thing, the difference is when you have a black hole, the string will not be distorted using this cast here, but it will be distorted towards the black hole horizon. So already this is a hint of the gravitational effect of the QQ bar potential of the probe we put. And if I want to translate that in the whole space of solutions, I can plot the length between the QQ bar, this distance, and with respect to Z0, Z0 is how deep inside the surface goes, and I can find that this is a plot like that. So it means that for any boundary conditions, let's pick up this, I have two minimal surfaces. One of them should be the one with the less, two extremal surfaces. One of them is the surface with the minimal area. Okay, so you have to pick one of them. This is how the phase transition happens in the finite temperatures. Okay, so before I compute the energy, I have to decide how I will regularize it. This is an infinite energy because I have infinite strings. So there are two ways to regularize it. One is I can pick up the Legendre transform maximum. This is basically motivated by the fact that I have different boundary conditions on the minimal surface in the transverse directions. So I want to make the transverse space-time direction to have Neumann boundary conditions, so I have to make it as depending the variation of the action to depend on the momentum. But this is good enough UV regularization scheme, but it doesn't take into account the infrared heat bath. Okay. The other equivalent at zero temperature, that equivalent regularization scheme is I will take out the infinite thermal mass of the single quark. So since I have infinite surfaces, infinite distance from the bulk to the boundary, I can take out one string, and this one string will correspond to the infinite mass of the quark. Now, if I do that in the usual ADS black hole cases, I will have some function here that depends on the metric, is known. But here I will have the lower limit will depend on the horizon of the black hole. This is an infinite integral. But here I don't have a black hole. So the question is, what plays the role of the black hole in the de Sitter geometry? And the answer is that I have a similar cutoff. So here, if I will find my single endpoint string solution, it looks like that. But at some point, it becomes causally disconnected from the boundary. So there is a point here, which I derive, but I'm not giving you the derivation. So there is a point here that becomes causally disconnected from the boundary, and this point exactly will act as the UV, as the infrared cutoff for the integration. So if you want to see the whole solution, this is my minimal surface, the connected string solution. This is the disconnected string solution. And you see that at this point here, basically here it's chosen to be at 1, At this point here, there is a cutoff, and I stop taking into account the rest of the string. Okay, so this is my slide before I finish. So, so then I can compute, since I know the regularization scheme, I can compute the energy of this, and then I can have the potential of the Q bar with the distance of the bound state. And you see that this becomes a utility state this form. So this is where the disassociation happens. So these are the points that it crosses the zero potential, and it's chosen such that when you cross the zero, the potential, the zero line, then you have a disassociation of the point of the bound state. So you increase the temperature, you have easier disassociation. So everything is consistent as if you have a finite temperature, a finite field theory on the flat space-time. Okay. So I'm flashing this for the spinning meson. This is a little bit. This then here just before I just took a static QQ bar. Then I make it to spin. So I add one more degree of freedom, and I would like to see what happens here. I'm not going to show you the details, but this is a little bit more involved computation, so it adds one more non-triviality on the thermal dependence on the horizon. But I will just tell you that this is the interesting plot, the energy versus the angular momentum, and you can see that indeed the energy of the bound state versus angular momentum, sorry. And you can see here that indeed there are two solutions for the same angular momentum. That means that as you increase the angular momentum for the rotation, there is a maximum angular momentum that is here, and then the bound state dissociates. So this is again a hint about the thermal behavior of the QQ bar bound state. So just flashing the conclusions. So we have used the Sitter equivalence, and you have had some non-local observables. But the Sitter heat bath is in many aspects qualitatively equivalent to the heat bath of field theories with black hole dual from the perspective of the probe. And the effective mechanism that the thermal effects are produced is different, at least from the gravity side of Q. There's, in the usual flat space theories, we have a black hole horizon. In our case, we have the expansion of the space and the causal structure of the string solutions. So thank you.
Any questions? System, how about you use black hole?
So it doesn't have black hole, so that's a good thing. So the expansion of the system plays the role of the black hole. So effectively, if you do the computations, you see that the expansion of the space plays the role of the black hole. So it's an effective black hole that can go to action. Let's say.
I mean, how about you introduce a real black hole?
Oh, you can do it. Yes, you can take. This is the work that has been done by Rangamani, Hubeni, and Ramston. So you can do time compactification as usual. You can do compactification along time, and then you have a black hole.
So is there any different from this effective black hole?
In difference in which sense?
Yeah.
When you have a black hole, you don't see the horizon. You don't see this horizon. So you see the temperature of the black hole. Yes.
So, no question? No question, let's take speaker.
Thank you.